All right, so a person is running around an elliptical track backwards. That's clockwise. Like, I don't think they're actually going backwards. Like, they're running forwards, but they're going clockwise around the elliptical track. The equation of the track is this. Okay. When the person is at this point, her x-coordinate is increasing at 6 units per minute. What? This is increasing? That means this is a rate. Because it says increasing. Her x-coordinate is increasing at 6 units per minute. So write it like this, dx dt, because that's the x-coordinate. Describe how her y-coordinate is changing. Right? How is the y-coordinate changing? That means a rate too, isn't it?
Yes, it's changing.
Yes. So that would be dy dt because it's saying how is the y-coordinate changing? So we're given dx dt. We have to find dy dt, and we're given an x and a y. Labeling all my numbers is really helpful. So is there an equation that I can get a dy dt out of?
Yeah, with respect to c.
So we got 4x squared plus 25 y squared equals 200. So what would I have to take the derivative of this with respect to? T. So we got d over dt. So we do the first one. We get 8x squared, no, just x, and then dx dt plus 50y dy dt. And then what's the derivative of 200? 0. Okay. Do we have an x? Yes, it's 5. Do we have a dx over dt? Yeah, it's 6. And do we have a y value? Dose. Then we have dy dt, and we just have to solve for it. Okay, 8 times 5 is 40, and then 40 times 6 would be 240. So I get 240 plus 100 dy dt. I got to subtract 240 from both sides. I get 100 dy dt equals negative 240. I divide both sides by 100. I had dy dt. What's that divided by 100? Wouldn't it be negative 2.4 because you moved the decimal twice? And what is this? Units per minute. There you have it. Now, if it's changing by a negative rate, the y value is increasing or decreasing? Decreasing? Yes. Okay, just to recap what we just were talking about. Once we got this written down, this part wasn't difficult. The calculus part wasn't hard. It was reading it. It was understanding what this problem is asking. Okay? So, this is like, I think, the first number that really clued me into on what I was doing. Okay? Now, I circle it, usually. I always circle the numbers. I didn't circle these ones. But increasing told me, hey, this is a rate. But there was also the units, or the units for the number 6. The 6 said 6 units per minute. Because it says per minute, that clues me in on that this is a rate right here. Okay? I labeled it too, dx dt. All right, now that helped me out later down the line. I knew it was something over dt, and I chose dx over dt because it says it's an x-coordinate. Then it says describe how her y-coordinate is changing. Because it says changing, I know we're looking for a rate. And because we did dx dt, dy dt is what we're looking for. That's what it led to. Okay, so let's do letter B. It says, can she run in such a way that her x-coordinate changes at a constant rate? Her x-coordinate changes at a constant rate. Now let's just think about this like without math really quick. All right, let's say this is our ellipse. This is our track right here. Okay, can she run in such a way that the x changes at a constant rate? Now think about this. What is constant right now? Like during this event, she's running. What is constant? I think someone said it. Did someone say her rate?
Yeah.
Yeah. When she's running, like she's running at a certain speed, her speed's not changing. But when we go around this line right here, we're going around this at a constant speed. The x-coordinate is like barely changing right now, right? And now the x-coordinate is changing a lot. Is the y-coordinate changing? When I'm running this straight part of the track? No, y-coordinate is not changing. Now the y-coordinate is changing. Is the x-coordinate changing very much? No. Okay, so the rates are changing at different rates. Whoa. The rates are changing at different rates. So, can she run in such a way that her x-coordinate changes at a constant rate? Oh, she's going around the track, right? Ooh, and I went clockwise. Okay. She's going around the track. Can she run in such a way that it changes? Well, I mean, maybe. If she runs really fast around this curve, right? Yeah, it'd have to be really, really fast. I would say it's not physically possible, especially too because at first when she's running on this part of the track, her rate is positive, but then when she's running on this side of the track, her rate is negative, and so at one point, her rate has to change directions. There's a positive, and then there's a negative, and so I would say no, this is impossible, and then we gotta explain it in such a way. No. And I'm going to say simply because her rate, her x-coordinate rate, I think I gave a different answer on my solutions, changes from positive to negative. All right, that's like a 1 point question, maybe 2. Probably 1. Get to see, it says the inside of the track is the heavily wooded area, and she cannot see through the woods. There is a bear standing on the outside at point 80. And we got a little illustration right here to help us with this explanation. When she is at the point 52, can she see the bear? Explain. All right, so let's think about this for a second. Here we have our ellipse, and the runner is currently at 5'2", and we're trying to find out if she can see the bear. Well, this is a tangent line, okay? Now, I don't know, all I know is the bear is standing at 80. I don't know if 80 is after the x-intercept for the tangent line or before the x-intercept for the tangent line. So our goal here is going to be to create an equation for this tangent line and then find the x-intercept to see if the 80 is right here, in which case the runner cannot see the bear, or if the 80 is right here after the x-intercept, in which case the runner would be able to see the bear. So the tangent line is y minus f of a equals f prime of a, which is our slope, times x minus a. So we know f of a, that's 2, and we know a, which is 5. So if I were to write that a different way, we need a f of a, and that in this problem is 5'2". That's where the runner is at. That's where we're going to find the slope at for our tangent line. Now the next thing we need is the slope. Now in order to find the slope, we need to have the derivative. Now earlier we took the derivative of this function, but last time we took the derivative with respect to t. Now we're going to have to take the derivative with respect to x so that we can find the rate of change for this ellipse. We need dy over dx. Now to get dy over dx, we have to take the derivative with respect to x. dy is your rise, the vertical change, and dx represents your run. That's rise over run. Okay, so we're going to take the derivative of this with respect to x now. So we have d over dx. All right, we get 8x plus 50y, and because we're taking the derivative of x, not y, we're going to multiply this by y prime, or dy dx, and that equals 0. Now, dy dx is what we want at 5, 2. Since this problem doesn't ask us to find dy dx, I'm just going to plug the point straight into the x and the y. So I'm going to plug 5 into this, and I'm going to plug 2 into that to get 40 plus, that would be 100 dy dx equals 0. Now if I get the dy dx alone, which is what we want, that's going to give us our slope. We get the dy over dx alone. Let's subtract the 40 from both sides first. And then we'll divide both sides by 100. Let's get this other stuff out of the way. And once I do that, I get my dy dx alone. Dy over dx, that's the slope at 5 over 2. That's what this guy represents. Slope at 5 over 2, or 5 comma 2, is going to be, let's see, let's cancel out those. We're going to get negative 2 over 5. So let's plug that dude in. So we have, I'm going back to this. I'm going to plug everything in. We have y minus 2 equals negative 2 over 5, x minus 5. All right, so this equation right here defines this tangent line. Now, if we want to find the x-intercept, we just have to plug 0 into this guy right here. So if I'm finding the x-intercept, that means I plug 0 into the y. So now this y is gone. I just have negative 2 equaling that. Let's get the x alone. So let's distribute that fraction over. We get negative 2 over 5x minus, that would be negative 2, because, 2 over 5 times 5, the denominator would cancel out. Just make the 5 into a fraction. These would cancel out like that. And so I'm left with negative 2, or negative 2, which is a positive 2. And then I would have to subtract 2 from both sides. So I would get negative 4, negative 2 over 5. And I would multiply both sides by the reciprocal of this function, which would be 5 over 2. Or we can do it in parts. We can multiply by 5 first, and then we divide it by 2. That's a negative 5. So it's positive 20 over 2, which means x equals 10. This point right here is 10, 0. That means that is not 8, 0. This is 8, 0. And so if the runner's line of sight sees only 10, 0, the runner cannot see the bear. The bear is inside right here. The runner cannot see the forest and see the bear. So because her line of sight sees the coordinate 10, 0, the runner cannot see the bear. And that's what you would want to say or explain for this problem. I wrote, I think that you could write your explanation really simple like this, because it's kind of assumed here with all the things that I wrote. You can see that since the x-intercept is 10, therefore the runner cannot see the bear. This is the evidence. We don't have to say, oh, because you can't see through the woods, because that's already stated up here. And we don't have to say that the point 10, 0 is beyond 8, 0, because that's a given. Everybody knows that. So that would be the end of your problem.